So today we are going to start lecture 47 on response surface method, and I am Dr. Ranjan Ganguly. Now typically we have talked about response surfaces in a very general sense as coming out of the classical approach to response surface developments for products and processes and dealing with experiments. But when we use this response surface method in optimization, we have to keep in mind that response surfaces are only valid in a small neighborhood of a given point. So we can say that there is a larger space here given by O, and typically we create a response surface around some point, for example given by X, and the response surface corresponding to this point is R of X. And this particular response surface is only valid in a small neighborhood of X. Now the actual optimal point may lie at X dash, and therefore we cannot get this point X dash if we are only restricted to this region R of X. Therefore what we do is that we find the best possible solution within this region, and it's very likely that it's going to lie somewhere on the boundary of this particular region R of X. Then we take that point as the new starting point. We create a response surface around this point, and we keep doing this process till we finally get a response surface here, R dash X, and we converge to some point Rx dash. So essentially what this means is that if you are going to go from a point X to a point X dash, you need to create a sequence of response surfaces. So at a very generic level, if you are at point X and your actual optimal solution is at point X dash, you will need to have a path to this particular point using a sequence of response surfaces. Now typically this R is a subset of this O, which is the giant set here, and when you are dealing with polynomial functions, this R is typically small. It's called a local response surface, local metamodel, or local surrogate. However, there are also global methods where you can actually develop metamodels which are valid in this entire region O, and those would be based on different methods such as Kriging or neural networks or Gaussian processes. So we see that typically when you want to use response surface in optimization, you need to apply this method sequentially. So essentially we can think of these cubes or spheres within which a response surface is valid, which is created by the CCD or the FCD type of designs. And these cubes or spheres can be thought of as the trust region where the response surface is valid. So recall, in a trust region type of situation, that's the region of the design space where you actually trust the approximation you have developed, or the response surface you have developed in this case. Now you need to put some kind of move limits or constraints to limit the search when you are using response surfaces, because remember that response surfaces are not valid globally, and therefore their movement has to be restricted to the region of the space where they are likely to be valid. And again, this process of selecting this move limit or constraint is more of an art than a science. I would say that for most engineering problems, something like 10 to 15% of the current point is the maximum to which you can let the problem go, or that should be the level of move limits which essentially constrains the design space to that region R of X. Now whenever you are dealing with simple linear move limits, then of course we have seen that the face-centered design is a better choice than the spherical constraint. However, using spherical type of constraints such as the CCD based design lets you have a larger design space. It also gives you a near rotatable design, and that has some theoretical good points going for it. So let us go back to our CCD problem and frame it as a problem to be valid within a trust region. So recall that our function to be minimized is a quadratic response surface. You have the constant term, the linear term, the curvature term, and the interaction terms. And all these regression coefficients beta 0, beta j, beta jj, and beta ij. And essentially, you minimize this particular function subject to a constraint. And here this constraint is essentially the equation of a hypersphere or a sphere, which has k dimensions. So if it's a circle, it would simply be x1 square plus x2 square is less than equal to k square. If k is 2, you know that this is going to be 2 here, and so you get the basic or simple problem. Now in more general cases, you essentially get this equation out here. So here one of the issues is that you do introduce a nonlinear constraint into the problem. So that is something to keep in mind, and essentially now you have radius of this circle is 2, and therefore the actual distance is root 2. So this is really a nonlinear optimization problem, can be solved using KKT methods or numerical methods. Now if you are dealing with the FCD, your move limits get simpler. So essentially that is one of the advantages of the FCD, is that you again minimize the second order response surface with all the different regression coefficients which have been found by the curve fit, and now you subject it to essentially a square or a box within which this particular response surface is valid. And therefore here you have linear constraints and a nonlinear function here. So in certain situations this kind of problem is simpler, and therefore you can use several of the methods we have developed for quadratic functions and linear constraints in this case. Now once you have obtained this response surface which is valid in this small region, you can find out whether it has got a stationary point using either KKT conditions or a numerical method. Now any of those plethora of numerical methods we have studied before can be used. This is of course a constraint optimization problem, so you have to address the constraints using KKT conditions, which is using Lagrange multipliers, or you have to address them using penalty, barrier, or one of the quadratic programming or CST type of methods. Now typically if your optimal point lies within that region R of x, then your stationary point could be a minimum, maximum, or saddle point, but what you are looking for is actually a minimum point. So if you have posed the problem well, you are likely to get the minimum point. Now in most practical situations, the minimum point in the trust region will lie on the boundary of the feasible region, and this will generally continue until you are very near the actual optimal point, in which case you may actually get a stationary point which lies within the region R of x. So if you recall the problem we started with, where the particular optimal point was x dash, then the response surface towards the end would have this point x dash lying within the trust region. But in most cases, if you are still moving in the design space, you will go to the end of this particular trust region, and which is going to be the boundary of the feasible region. So essentially your constraint is likely to get active at that boundary. So the choice of appropriate move limits will play a very important role in the response surface method. So again, this is more an art than a science and requires domain knowledge for the problem. Now one very important concept to remember, and this is where some neophyte researchers make mistakes, is that the optimal point of the fitted model is not the optimal point of the actual computational model. And whatever fitted model you have developed is just a guide for the actual function. And therefore what you need to do is you need to take the design predicted by the fitted model or the point predicted by the fitted model, plug it into your actual simulation code or function, and get the values of the function at the point predicted by the response surface. So this is something which is very important to remember, that the response surface is being used only as a guide. You run the simulation code at the optimal point predicted by the response surface to get the final optimal design. And therefore, if people have issues regarding your response surface, your fit, your functions, your vectorial designs taken, and so on, all this can be resolved if you get a good solution at the end of this process in terms of the final simulation code. So you're not relying on your response surface for the end result. You're only using the response surface to guide your path. Now, generally, if the final design you get is relatively better than the design you started with, then you can use this new point for your optimal design. So response surface is being used only as a guide here, and any final decision you make about whether the optimal point is to be used in a realistic design should be confirmed by running the simulation model at the particular point predicted by the response surfaces, and you also need to check if any constraints which are there in the problem, physical constraints, are actually satisfied at this point, because these need to be satisfied by the actual simulation model or the experiment concerned. Now we also see that because of the validity aspects of the response surface method in optimization, you need to move slowly through the design space by taking small steps, and therefore it is best to perform response surface based optimization in a sequential manner. So you could start from a point far from the actual minimum point, develop a CCD which is valid in the neighborhood of the starting design, and then move on to the next point and so on. So typical optimization methods such as those based on KKT conditions or numerical methods can be used to find the minima using the CCT design. The new design can then be used as the starting design to move further in the design space. So this is very important, is that the new design, which may actually lie on the boundary of the feasible region of the first design, is then taken as the center point, and then you again take a perturbation around this center point of plus minus 15%, and you move further in the design space in this manner, while restricting each move to within the region of validity of the response surface, which you determine by your perturbation in the high-low system. So the response surface method can be pictorially thought of as moving in the design space using these quadratic fits. And again, because most nonlinear functions can be approximated as quadratic fits in a small neighborhood of the point, the response surface method would come out quite well for most actual situations. Now, as you make more and more progress in the design process and optimization, one of the tricks you learn is that you can slowly reduce the perturbations as the response surface progresses toward the optimal point. So you may start with some perturbation like plus minus 15%, and you may slowly lower it to plus minus 10%, and then finally to plus minus 5%. So this will make sure that you get the optimal point to quite a good level of detail. Now, some people say there is a similarity between Taylor series and response surface method, and conceptually it may seem like that, but Taylor series approximation is valid very locally because it uses derivatives at a given point. Whereas one can think of response surfaces as very rough kind of Taylor series systems. You are taking large jumps in the design space by doing curve fits. So in some ways there is of course a relationship between a curve fit and the Taylor series in a certain limit type of way, but these are quite different. But you could think of taking very rough Taylor series and also doing response surfaces. So I think some researchers such as Van der Plaats have commented that this method was actually being used a long time ago but it was in the garb of these kind of rough Taylor series methods, and then later it became more solidified because of the statistical background which came from response surface methods, and then that helped us develop this DOE type of framework which takes 15% or 25% perturbations from the center point rather than the 1% or less type of perturbations which are taken typically in the Taylor series. Now, one of the advantages of response surface based designs is that any designs you obtain during the process are all useful provided they satisfy the constraints. And sometimes if your method works for a few shots and then it has some problems in terms of constraint resolution or in terms of convergence, you can still get a better design than the starting design. And therefore, several times this response surface based optimization can be used as a procedure where you play around with the actual code which you have, you develop these response surfaces, maybe you take 3-4 sequential runs of the response surface and then you get a good solution. So for most people who are working in design situations in companies or in different places which actually do design, this is quite a suitable solution as far as their group is concerned, because what people are looking for is a better design. Generally, people who are practitioners are not so much interested in the fact that the gradient is 0 or the second derivative matrix is positive definite at the minimum point. They are mostly looking for a better design. Now, one thing I should mention before closing is that the simplicity of the response surfaces, which is because of their use of the polynomials, makes it very useful for use with stochastic optimization methods. Now, stochastic optimization methods have a good point in that they are multimodal, that is, they can find a solution of problems which have many minima. But one of the things which restricts them is that they can take a lot of computer time because of function calculations. But now that your functions are simple polynomials, it's not a big problem to calculate these particular values, and therefore any kind of stochastic optimization methods can be used here, like particle swarm or genetic algorithms or Firefly and so on. So again, that is something which is useful. For example, we have solved a problem once with the rotor design variables with composite ply angles. And here the top level problem of designing the rotor blade was solved by response surfaces. The bottom level problem of finding the composite beam was done using GA, because here discrete design variables are involved. So the top level was in terms of polynomials of second degree. The bottom level was completely discrete. So again, you can split any problem in these two levels, and this is also sometimes known as a multi-level optimization method. So again, response surface can lead you to many situations where you can convert a very complicated helicopter analysis code into a set of functions, and then you can use those functions to essentially drive one more code which tries to find the best possible ply layup for a given problem. So again, the main thing to keep in mind is that response surface let you decouple the analysis problem and the optimization problem, and that has led to its widespread use in the companies, in the industry, and now there are several softwares and small companies which essentially help you use response surface in a more generic manner. So this terminates lecture 47. I will come back to you in my next video, where we are going to further enhance the response surface method and discuss some of the designs beyond the 2K, the CCD, the FCD, and so on. I'll see you in the next video.